So our guest speaker today is Dr. Michael Busch. Michael is a research scientist at SETI Institute, which stands for Search for Extra Terrestrial Intelligence. He is an expert on near-Earth asteroids. He has a particular interest in the shape, spin state, internal structure, and history of individual objects, especially spacecraft mission targets and potential Earth impactors. Michael completed his PhD in planetary science from Caltech and did postdocs at UCLA at the National Radio Astronomy Observatory under the Jansky Fellows Program before starting as a research scientist at SETI in 2013. Michael will present his talk, Near-Earth Asteroid Space Missions and the Impact Hazard. So please welcome Dr. Michael Busch.
All right, thank you. Can everybody hear me? All right. So, just to make something clear, SETI stands for Search for Extra Terrestrial Intelligence. That's actually very little of what happens at the office. The rest of us are doing more general planetary science, astronomy, geology. So I'll be talking about some aspects of that tonight. Something I want to make clear, very little of what I'll be talking about is my own work. I'm summarizing work by a large number of people over the past several decades. Hopefully I can manage to do that in a reasonable fashion in 60 minutes. We'll see. If anything I say is incomprehensible, please interrupt me. I'll try to clarify. If anything I say is really boring, please bear with me. I hope it'll get more interesting. So this is a plot of the inner solar system out to the orbit of Jupiter as of this morning. And this plots everything we currently know about it. Now, we projected everything down onto a single plane. We're effectively looking down on the solar system from way above the sun's north pole. The Earth is here. Mercury is right about there. I don't know if you'll be able to see it later tonight. Depends on how much scattered light there is, humidity in the atmosphere. Venus is over here. Mars is over this way. Jupiter itself is out there. Now, all of the other dots are different categories of small bodies. The green dots between the orbits of Mars and Jupiter are the main belt asteroids. These dark blue clouds here and here, which may be hard to see, are the Trojan asteroids that share the orbit of Jupiter, 60 degrees in front and 60 degrees behind the planet. And then the light blue dots are comets passing through. But tonight I'm focusing on all the red objects. So these are markers denoting the locations of all the near-Earth asteroids. Now, a near-Earth asteroid is defined as something that comes within 50 million kilometers, or about 30 million miles, of the Earth's orbit around the Sun on its own orbit around the Sun. So, while these things can, and some of them are passing near the Earth, right now, most of the time, any given object is very far away from us. Some get closer to the Sun than Mercury, others get further away from the Sun than Jupiter, although not by much. Now, the near-Earth population is not primordial. On the time scale of a few million years, the orbits of these things will change, and they won't be near-Earth objects anymore. So they have to get constantly replenished. It's getting replenished by objects from the main asteroid belt, getting pushed onto eccentric orbits that bring them closer in to the Sun, such that they become Earth crossing. So the near-Earth population that we're sampling here, there's about 13,000 objects marked, is a way of studying objects that were previously out in the main asteroid belt, but now they're much closer to us and much more easy to examine. The main asteroid belt is a remnant of planet formation, material that never piled up to build something like Mars or Jupiter. So this gives us a way of studying stuff that was happening in the solar system 4.5 million years ago, when everything was getting assembled out of the free solar nebula. This is interesting scientific motivation for studying the near-Earth asteroids. We'll get to the other motivations later. Now, things may look kind of crowded there. I should make something really clear. There's lots of objects, but there's much, much more empty space. I've made the markers thousands of times larger than the dots, than the objects they actually represent, because I can only make dots so small with finite-sized pixels. And otherwise you wouldn't be able to see them. There's about 1 billion miles of space represented from one side of the screen to the other. There's hundreds of thousands of objects in the main asteroid belt, and then, as I said, more than 10,000 known in the Earth population, but they're about as thinly spread as if I have a grain of dust in one side of this room and a grain of dust on the other side of the room. And we understand this intuitively. You look out at stars at night, you see the stars. You don't see asteroids blocking everything. So there's lots of stuff out there, but there's a lot more empty space. We see stuff that looks like this. There are 6 comets down here. They are very dark colored. They are almost invisible right now, but that's okay because I'm not talking about them anyway. Focus on all the other objects here. So these are different asteroids that have been visited by spacecraft so far at different times. Now, something like Letitia, which is a main belt asteroid, is about 130 kilometers wide. That's about 4.5 billion years old. It probably formed in the early solar system. But you'll notice it's lost a large fraction of its volume since then. So because of Jupiter, primarily, and also the other planets, scattering their orbits around, when asteroids hit each other, they're traveling very fast, many, many times higher than their escape speed from their own gravity. Result is that collisions tend to remove material. Letitia has managed to survive 4 billion years. Something a bit smaller would not have. So all of these smaller objects that we have visited with spacecraft at different times are remnants of previous collisions between other asteroids. So they sampled different types of material. The tilde is in fact about that dark colored because it contains lots of carbon compounds. Steins, this one here, is very light colored rocks. But even though they're sampling different geology from the early solar system, they all have a similar property that these are all the reaccumulated debris of previous asteroid-asteroid collisions. So the asteroid belt is slowly grinding its way down into dust, and we're seeing that whole process happen. Something like Toutatis here might last 100 million years in the main asteroid belt. The object that we're seeing now is going to be 3 or 4 generations down that collisional cascade from whatever object it was originally in. Now I'm going to zoom in even further on that dot. That's the asteroid Iokawa. These 3 that I've outlined are near-Earth asteroids, so I'll talk more about spacecraft missions to them in particular in the second part of the talk. But briefly on Iokawa, this is what it looks like. Now this is 540 meters, about 1/3 of a mile from one end to the other. It's a pile of rubble. So this is what you get when you run asteroids into each other repeatedly. Lots and lots of broken up bits sitting on one another. You also notice that it is not round, and neither were any of the other asteroids I showed you. Reason for this is rock has compressive strength, even such a massively fragmented pile of rocks as this. And gravity is very, very weak for an object this small. You don't stand on a mountain and have its gravity pull you in as much as the Earth's gravity is pulling us towards the floor. But there is a very small amount of gravity here, 10,000 times less than we have in this room. And under that low gravity condition, you don't need much strength at all to keep this 100-meter wide object from slumping down onto the rest of the surface. So it's a very weird physical environment. Our intuitions aren't really calibrated for this. We don't think of things like electrostatic charge mattering for geology. But on something this low mass, low gravity, that actually happens. You'll notice all the fine-grained material that's settled in here and more larger blocks. This is a gravitational low spot. But there's no wind, there's no atmosphere. So how did the dust get down there? It ends up that it gets charged by the solar wind coming in, very thinly dispersed protons. The dust grains levitate off the surface and bounce over and land in the low spot. Again, very weird physical environment. Very different physics dominating the geology than what we're used to. So there's another scientific motivation for studying these things. Very unusual physical situations. Now, there's another motivation, in addition to early solar system and weird physics, which is already given away by the title of this talk. So, I mentioned the Earth asteroids have a lifespan of a few million years in their current orbits. What happens to them? Well, they can fly by Jupiter very close and get scattered out of the inner solar system completely. Their eccentricity can increase so much that they come very, very close to the sun and literally boil into space. That happens more often with comets because they're mostly made of ice, but asteroids can get destroyed that way. We see a couple that are doing so. The asteroid can get hit by another asteroid and get broken to pieces. It can get spun up by sunlight shining on the object and spin up to the point that it flies apart because the gravity is so low. Or it can hit a planet. Sometimes that planet is the Earth. This motivates a lot of interest in studying the near-Earth asteroids because they can and do hit. So here's a few examples of asteroids hitting the Earth. Many of you may have seen this photo or the video that it's a part of, or many of the other videos that are available. So this is Chelyabinsk, a city in Russia. Population about 1 million people. On February 15th, 2013, early in the morning, this is UT time indexed off of London. This is a couple of hours further east, so it was just about sunrise. An object about 15 meters across came in. Now that's going to fit, not quite fit between the floor and the ceiling, because this is a fairly tall room. But it's coming in, and it's orbiting around the sun. It's moving at several kilometers per second relative to the Earth. It falls through the Earth's gravity, it speeds up, and then it hits the atmosphere. Now it's coming in this case, at a fairly shallow angle, but it keeps going through more and more atmosphere. And it's rapidly converting its own kinetic energy into heat, light, and sound. The energy deposition raises exponentially because it's running through more and more air as it comes closer to the surface, until eventually it deposited most of its energy in a fireball, about 10 kilometers above the city. Now, it was very briefly as bright as the sun. This got lots of people's attention. This is a security camera that happened to be looking in the right direction to see it, but there's also lots of videos from dashboard cameras, people driving to work, cell phone cameras, people suddenly turn them on to look at the fireball. But this caused a slight problem. What do you do when you see a really bright flash in the sky? Some people are saying duck. That's a good choice. A lot of people ran to the window to see what this bright flash in the sky was. I mentioned sound. Shock waves travel at the speed of sound. It hits the ground between 30 seconds and a few minutes after the fireball, depending on where you're standing. It blew out windows across the entire city. About $30 million in damage. Automobile glass is strong enough that didn't break, but a lot of buildings' windows weren't. So there are about 1,500 people injured, mostly from broken glass. Some glass getting blown into their face, the window blew in, other people stepping on the glass afterwards. Nobody died, but it was a very near thing. A couple of people were thrown down flights of stairs. Now, initially there were several thousand tons of rocks up there. That all disintegrated pretty thoroughly. Most of the mass got turned into vapor, very fine-grained dust. Some small amounts were dropped in rocks meteorites that scattered across the town. This is one small sample, which you all can look at after the talk, if you want to. Various other pieces retrieved afterwards. The single largest piece was only a few hundred kilograms, so it's very thoroughly disrupted. Now you can go find lots of those for sale on the internet. There's lots of fakes out there because people try to make money to recoup the cost that their windows got broken in. So be careful if you are buying meteorites. Now something like Chelyabinsk happens somewhere in the world every 20 to 30 years. The last time was in the 1960s over the South Atlantic Ocean. It was only noticed because early satellite monitoring was working at that point. Most of the time, these don't cause any problems, except when they're over a large city. We'd like to know about these, if we could, hours or days in advance, to at least tell everybody to stay away from the windows. Now, larger things happen less frequently. That collisional cascade I mentioned ensures that there's many more smaller asteroids than there are larger ones. So this is a place called Tunguska, which is further east in Russia. At least you think that Russia's getting singled out here. It's a large section of the land surface of the Earth. And until we had the satellite monitoring, meteor falls over the ocean didn't really get noticed. But this is in 1908. The photo is actually from some decades later. On June 30th, 1908, an object bigger than this room now, 30 meters or so across, came in. Because it was so much larger, it got much lower down in the atmosphere before it stopped. The airburst was at a lower altitude, much stronger. it flattens trees over an area a significant fraction of the size of the bay. And something like that happens somewhere in the world every few hundred years, as best we can tell. But records more than 150 years ago or so get a little bit scattered. So there's some uncertainty there. And then there's this one. This is Chicxulub. This is the edge of the Yucatan Peninsula. This is the Gulf of Mexico. The town of Chicxulub is here. You can't see this crater on the surface. I say crater because here is an object that was several kilometers wide. It came down and it blew a hole more than 100 kilometers across in what was then shallow sea and is now hundreds of meters underneath the sediment that has been laid down over the last 66 million years. Now this became particularly notable in the 1980s. Louis and Walter Alvarez over at Berkeley were trying to figure out a problem. No matter where you go in the world, you will find rock. If you find rocks that are 66 million years old, you find dinosaur bones in them. Then there's a contact, and above that there are no dinosaur bones anymore, except for birds. And at that contact, there is a couple of distinguishing properties. There is ash, and there are little bits of meteorite. So some really large pile of rocks came down, and the climate disruption from that large impact caused a mass extinction. In the 1980s, people tried to figure out what this was, where this was, and eventually they found this crater buried at the right age and concluded this thing killed the dinosaurs. We prefer that this not happen to us, or anything even remotely close to that. So this motivated, starting in the 1990s, lots of efforts to find and just track and predict the orbits of as many near-Earth asteroids as possible. Please, there's something.
I was just wondering, is it the shockwave that blew out those trees of meteor, or is it the shockwave that hit the Earth?
So in this case, Tunguska, it was just small enough that the asteroid got stopped slightly above the surface. So the airburst here is 10 kilometers up. This was only a couple kilometers up. Right.
And that shocked the airburst.
This flat was flat on the trees, right. So the question is, did this hit the ground? For Tunguska, it did not. Something slightly bigger, coming more straight down, can hit the ground. Meteor Crater in Arizona, if anyone has been there, is what you get in that sort of situation. That was a slightly larger object than Tunguska, significantly denser. It happened to be made of metal. And it came nearly straight from vertical. So it went through less air before it hit the surface. So somewhere slightly bigger than this is where things get to the ground intact. Chicxulub impactor, it was so massive it didn't really care that the Earth had an atmosphere. It just plowed straight through and made a humongous hole in the ground.
Do you know the incident angle?
I do not. The question is the angle at which Chicxulub hit the ground. I don't recall the exact number on that one. One more question before I go on here?
For the Chicxulub crater, I heard that they discovered it by looking for the gravitational anomalies.
So what you're seeing here is actually a gravity anomaly map. So the Earth's gravity gets affected slightly by the rocks that we're standing on. Much like you have slight gravity near the small asteroid, you have slight changes in gravity if you're standing near a mountain, or if the rocks beneath you are greater or lesser density. So the rocks on top of this impact crater are lower density than the rocks underneath them, just because of the sediment that's being laid down. And so you can see this ring where the edge, the higher density rock, is closer to the surface. And for this particular type of impact, you actually get two rings, an inner and outer. And then the outer ring got partially eroded on this side before everything got covered in sediment. What you're seeing here is the rocks deep beneath you, measured just by walking over them with a very sensitive gravity meter. Geologists get cool toys. Okay, so we want to find as many near-Earth asteroids as possible. How do we do this? So initially this was done with photographic plates, surveying chunks of the sky, taking the photographic plates, processing them in the darkroom, and then having a human stare at the plate, take the same section of the sky, taken a couple hours apart, and switch them rapidly between one to the other, and figure out anything that moved. This is a really annoying process. It's also not very efficient, because photographic emulsion only picks up a few % of the light that hits it. gets converted into color, change in the dye. Fortunately, in the 1990s, CCD cameras became a lot better than they had been before. And very quickly, we became able to survey large areas of the sky, detect almost every photon that hits the camera, and with developments in computer processing, automatically survey the images and look for things that move. So that the human only has to verify this is indeed a real asteroid and not a satellite or an airplane flying through above the camera. This is a lot faster. And surveys have gotten progressively developed over the last 20 years now. Currently, the two most active are the Catalina Sky Survey in Arizona and the Pan-STARRS project in Hawaii. So whenever there's a clear night in either Hawaii or Arizona, they take a telescope and they survey a large section of the sky. And they go back to the section of the sky repeatedly throughout the night, and that lets them see any asteroids that are moving through that section that are bright enough to see. If you do this for long enough, you can find everything that's on an Earth crossing orbit. Now, there's a complication to this, which is that some objects are on orbits such that they spend most of their time closer to the sun than we are. That means they never get very far from the sun on the sky. That's a problem for these optical telescopes that are on the ground. You can't really do optical astronomy terribly well during the day. The sun is annoying like that. So there's been a project recently called NEOWISE, which is using NASA's Wide Field Infrared Space Explorer, the WISE satellite. This is a satellite that was originally designed for astrophysics, not asteroids, but it turns out to be really useful for this. It's orbiting out in space, and it's constantly scanning a loop around the sky every 90 minutes at 90 degrees away from the sun. So the Earth is here, the sun is here, WISE is looking that way. That's just a little bit closer to the sun than we can easily observe from the ground. So WISE has caught a bunch of asteroids that the ground-based surveys cannot find themselves. And between them all, we're currently discovering about 1,600 near-Earth asteroids every year, which is a lot of objects. That rate is expected to go up considerably because we're fortunate to have newer telescopes becoming available. Some of you may have heard of LSST, which is the Large Synoptic Survey Telescope. It's currently getting built in Chile. It has a couple of advantages over Pan-STARRS and Catalina. One is that it's a somewhat larger telescope. It's not getting used only for asteroid work, but it's surveying large parts of the sky at an appropriate cadence for this. The second is that it's in Chile, in the southern hemisphere, so it can see the southern part of the sky, which we cannot see fairly well from Arizona or Hawaii. So that way we can cover a lot of asteroids that we'd otherwise miss.
How many blind spots are in that percent of blind?
So the question becomes, what are the blind spots? Well, there is still a blind spot even for LSST, which is this area near the sun. So NASA does have a proposal pending to address that one. And that's a project called NEOCAM, the Near Earth Object Camera. That is inspired by WISE, uses much of the same technology, but instead would look this way, covering this whole section of the sky, and also that section of the sky on the other side of the sun. That way it covers most of the area of the sky that's interior to the Earth's orbit. So it could find those asteroids much more quickly than we'd be able to do from the ground. So the idea now is to find all near-Earth asteroids down to about 100 meters across within the next 10 or 15 years. And you need the combination of all of these new surveys to do that. If not, the current surveys can still do the job. It'll just take a bit longer. Now, initially, the surveys weren't intending to go down to the 100-meter size limit. The initial goal of all these survey programs, starting in the 1990s, was to find everything in the near-Earth population bigger than 1 kilometer across. I mentioned the Chicxulub impactor was 5 to 10 kilometers wide. A 1 kilometer wide asteroid is probably not going to trigger a mass extinction. Even something like Chicxulub is not guaranteed to do that. But a 1 kilometer wide impactor will cause very large disruptions to the climate for a few years' time, which is very bad for growing food. And it would have global scale problems as a result. So the idea was to check that there was no near-Earth asteroid bigger than 1 kilometer across that's going to hit the Earth in the next few hundred years. And that we have done. So this is the discovery rate of asteroids as a function of time. In the 1990s, I apologize, the text is a little bit blurry. But in the 1990s here, the survey rate jumped up because CCDs came in. And then steadily improvements in telescopes since then, survey rates kept on going up. This is only partial data for 2016. But initially we were focusing on those larger asteroids. I say we, I was not doing this stuff in the 1990s. My PhD supervisors were. The surveys discovered lots and lots of objects bigger than 1 kilometer in diameter initially, and then that rate steeply fell off. That's because we found everything on Earth crossing orbits that's bigger than 1 kilometer in diameter. We surveyed that whole space, where anything that's on with an orbital period of a few years, bigger than 1 kilometer, it will eventually have become bright enough at a time that we were looking in that direction in order to see it. So we can say nothing bigger than 1 kilometer in diameter will hit the Earth in the next few hundred years. That's good. There is one of these objects that has a potential Earth impact in 2880. I have not been able to rule that one out yet. It's a little frustrating.
But you don't factor in the gravity of other planets that they reflect these effects.
I will talk about that in the next slide. So, to finish up this question, why are we surveying for all these smaller objects? The answer is that we've become, particularly post-Chelyabinsk, understanding of the hazards posed by smaller objects. And down to about 100 meters in diameter, no matter where you are, the impact were to take place in the world, we would want to prevent that impact from happening, deflect the asteroid from an Earth impacting trajectory to a non-impacting one. But to do that, you have to have enough advance notice to build a spacecraft, launch it out to the asteroid, and do that deflection. That typically would require many years to do. So the idea is to find everything in the population down to that size limit. And then for smaller things, like the Chelyabinsk impactor, the surveys are designed to give us a few hours to a few days of advance notice the next time something like that happens. So in that case, you just tell everybody to stay away from the windows and go pick up meteorites after. For the larger ones, though, we want to have more advance notice. So far, we have not found any such objects that are going to hit the Earth. We keep having potential impactors, though. So here's the problem. We discover an asteroid. We measure its position on the sky now. We measure its position on the sky the next day, the next week. We only measure that position so well. We only know how fast the asteroid is moving so well. Now, we run its orbit forward in time. We account for the gravity of the Sun, which is the biggest effect, obviously. We account for the gravity of Jupiter, the Earth, all the other planets. We can account for the fact that there's a moon flying around the Earth, if it matters. We can account for the asteroid belt, which changes things a little bit because there's a bit of mass out there moving around. We know the dynamics of the situation very well. We don't know the asteroid's initial position and velocity well enough, at least with only a short amount of data. So we have situations like this. Early 2011, we found this object. We used to get a telephone number 2011 AG5. We give them phone numbers rather than giving most of them names because it's really hard to think of 1,600 names every year. So it was discovered early 2011. You run the orbit forward to 2040, and you find that the asteroid will be somewhere along this line. If it's over here, then we would have seen it moving a bit too fast, relative to what we actually observed over that week. If it was over here, then it would be moving a bit too slow for what we actually saw. So all we knew after 1 week of observing was that in 2040, so 39 years out, it would be somewhere in that line. And the Earth happens to intersect that line. So we now say there is a 1 chance in 500 of impact. But that's merely a way of quantifying our own ignorance of what's going on. Indicated procedures to go back as soon as we can and get more data, better constrain its orbit. So that happened about 20 months later. October of 2012, the group out of Hawaii used one of the larger telescopes for dedicated observations of this particular asteroid. Very precisely figured out where it was. 18 months of data, we can know its orbit a lot more precisely, and we can say it will be over here. The Earth is over here. There is no possibility of a collision in 2040 by this asteroid. And we can actually run the orbit out considerably further than that now, and it never hits the Earth. But we keep having cases like this, where asteroids are discovered, they have potential impacts, and it takes us a while to get enough data to rule things out. So that motivates actually a large chunk of my own research, because we want to try to understand these objects as best we can, including their orbits. So the way I personally help address this problem is using radar astronomy. So we have a high-power radar transmitter mounted on the Arecibo Observatory in Puerto Rico. Many of you may recognize that from its appearances as itself in Contact and as the villain's hideout in a James Bond movie a while back. Very dramatic location. You find a hole in the ground 1,000 feet wide and build a telescope in it. We send a signal out here, it goes out to the asteroid, the radar echo comes back down, and then we record it. We have a similar setup at the Goldstone Deep Space Network antennas, which NASA operates in Southern California. So we time how long the signal takes to go out and come back. That tells us very precisely where the object is. So this is only useful for objects that come near the Earth, and only for targeted observations. We can't use it to find near-Earth asteroids, but we can use it to very precisely determine the orbits of objects we already know. So for instance, I can tell you the asteroid 1992 UY4, its center is right about there. This is the half of the asteroid that the radar can see. And I can also tell you more precisely the fact that the object is shaped roughly like this. This is results a summer student and I have come up with over the past 10 weeks. 3D printing is fun, by the way. So we now know very precisely where this asteroid is. We can run the orbit out much further in the future. We've done the same for lots of other asteroids. At the same time, we're studying the near-Earth asteroid population and its properties. So I showed you Itokawa, which is what we call a contact binary, two pieces sitting on each other. Some asteroids have that shape. Some have significantly more extreme shapes, like 2000 RS11, which you see down here, which looks like this. I apologize to people in the back, but these 3D prints, you can take a look at them afterwards if you want. Other asteroids have satellites. So you have pieces of material that are traveling slowly enough, they can in fact remain in orbit around something that's only a few hundred meters across. So this is now a series of time exposures of an asteroid. So the asteroid, the primary, gets blurred out of rotation here. But notice these arcs. Those are satellite looping around. So now we have two asteroids here instead of one. This obviously complicates discussions of deflection. If you were talking about moving the asteroid, you have to now worry about two objects rather than just one. So all of this stuff together, the impact hazard, the scientific, early solar system, and odd physics motivations, have combined to provoke quite a lot of interest in sending spacecraft out to the asteroids and studying them directly. Because even with the radar imaging, there's only so much we can say remotely. So that's what I'll be focusing on for the rest of the talk. Various spacecraft missions to different near-Earth asteroids. Now, there have been quite a lot. I have not actually listed all of them on the slide because I only have so much space. So there have been 3 near-Earth asteroids visited by spacecraft to date. I had marked them earlier. Here they are again. The first one was Eros, which is the second largest near-Earth asteroid. NASA's Shoemaker spacecraft, which was originally named Near-Earth Asteroid Rendezvous, NEAR, visited Eros in the late 1990s, landed on the surface at the end of its mission. The next one was the Hayabusa spacecraft, which launched by JAXA, the Japanese space agency. It went to the asteroid Itokawa. I showed you one side of it before. Here's the other side. You'll notice again more blocks scattered around of various sizes. Hayabusa briefly landed on the surface of Itokawa, picked up a small quantity of dust. That got returned to Earth, dropped in a capsule in Australia, and is now getting analyzed atom by atom in laboratories in Japan. Motivation for doing asteroid sample return here is that if we have meteorites, bits of asteroid, we don't know exactly where they came from. We might be able to tell in some few cases which object they came from, but it doesn't tell us the exact environment they were in. They've also been pretty heavily processed by falling through the atmosphere without any protection. So go out there, grab a rock, we know where it came from, bring it back inside a capsule shielded from the atmosphere, we learn a lot more about the objects. Their third asteroid mission was Chang'e 2, which is launched by China. This actually was not initially an asteroid mission. Chang'e 2 is part of the Chinese lunar mission series. It was mapping parts of the moon for the Chang'e 3 lunar lander, which landed a couple of years ago now, and also the Chang'e 5 lunar sample return mission, which will launch next year. Chang'e 2, though, had a little bit of extra fuel in its tanks when it was done with this mission. They flew it out of Earth's orbit completely, very slightly above Earth's escape velocity, just enough such that when an asteroid called Tutatis was flying by, they were in just the right spot so the asteroid could fly by the spacecraft. And they took a series of pictures during that whole flyby. We had observed Tutatis with radar repeatedly before, so we knew exactly where it was going to be, which is good because they ended up flying the spacecraft right about there. If our ephemeris hadn't been good, there would have been a significant chance of a collision. Now, they were supposed to fly slightly further off to the side here. So, again, good that our trajectories were accurate in this case. And I can tell you from all this data, none of these asteroids can hit the Earth in the next several hundred years.
So they must have matched speed.
No, they did not. They flew by. The question is, did they match the speed for Tutatis? They flew by that asteroid at 10.7 kilometers per second. So the asteroid's orbit, in this case, goes out into the main asteroid belt. So it's going very, very quickly relative to the Earth, so it has enough energy to fly out far away from the sun. So it blazed by the spacecraft. They didn't image it as the asteroid came in, because they couldn't turn the spacecraft around fast enough. They locked the spacecraft aiming this way, and the asteroid went like that. So this is the rear-view mirror view of Tutatis as it flies away from the sun. Now, those are the past asteroid missions. There are a bunch more that are happening. There are two that are currently going. One is Hayabusa 2, which is a follow-on by JAXA to Hayabusa 1. It also has a lander provided by groups in Europe. That will go to the asteroid Ryugu. It's currently in flight. The second one, which I'm calling current, is OSIRIS-REx, which is launched by NASA with some contributions from the Canadian Space Agency. OSIRIS-REx will go to the asteroid Bennu. These are both asteroid sample return missions, sampling different reservoirs of material from the early solar system. So we'll have pristine samples from the silicate rocks that make up Iokawa, and then we'll have pristine samples from the rocks that make up Ryugu and Bennu, which are different parts of the early solar system. So that's the science motivation. There is an impact hazard motivation, because we observe Bennu with radar imaging repeatedly. We can say it looks like this. The colors here represent the angle between gravity and the surface at every point on Bennu. You can see it's not round. But it's important to note there's these very flat areas around the equator. That's important for landing the spacecraft because you don't want your very expensive spacecraft to land and get stuck by running into the side of a wall. So you want to land it in the flat spots. But we also know from the radar imaging Bennu's orbit very precisely. It has a series of potential Earth impacts, starting in 2175 and running out to 2200. Its orbit precesses around the sun very slightly, and during the 25-year window, it's within 1 Earth radius of the Earth's trajectory, so impacts are possible. We say there's one chance in 3700 of impact by Bennu. Again, that's quantifying our ignorance. We need better knowledge of how it's moving. So OSIRIS-REx will fly out there, and in addition to telling us a lot more about the object, it'll very precisely measure its trajectory, and we'll be able to rule out those impacts. So this is how we address the asteroid impact hazard. Yes?
You said none of these are going to hit Earth in the next 100 years.
So this one is not, it's almost certainly not going to hit the Earth.
Okay.
We just cannot rule out the possibility that it will hit.
But I was talking about the other three.
These three cannot hit the Earth in the next several hundred years.
Is it possible that they collide with another asteroid and changes its...
So there's some unavoidable uncertainty in our predictions.
Okay.
Asteroid-asteroid collisions of that magnitude are pretty rare. And in order to cause that large of a deflection over a short time scale, they would blow the asteroid to pieces, which actually gets relevant for discussions of asteroid deflection. So I'll talk more about that a few slides down. Now, there are various other asteroid missions people have proposed or are developing. I've listed 3 of them here. I'm going to talk about these 2, AIDA and the Asteroid Redirect mission, because they propose to demonstrate asteroid deflection, among other things. So that if we do hit this 10% or so probability that we find something that's big enough in the next few hundred years that we want to deflect it, these 2 missions propose to demonstrate ways to do that. So that if we ever actually have to do this for real, we'll have confidence we know how to do it. So those are both by NASA and ESA. There's also a Chinese asteroid mission that's getting developed following the success of Chang'e 2. That one's interesting. I apologize for the screen getting cut off. There's a name down here of an asteroid called Apophis. Apophis is kind of notorious because it makes a very, very close Earth flyby in 2029. It will get closer to Earth than many satellites that are currently in orbit. It will not hit. But because it passes so close to the Earth once, its orbit loops back, and eventually it comes near the Earth again. And because that flyby to the Earth perturbs its trajectory so much, right now we can't rule out impacts by that one further than about 2070. That will be ruled out almost certainly if we get better information on its orbit, which this mission would provide.
How close to me when it says close by in 2030? Is that Leo?
So the question is, how close does it get? It gets closer, in 2029, Apophis will get closer to the Earth than the geosynchronous satellite belt, which is where a lot of satellite TV antennas are. It will pass safely through the orbits of everything currently around the Earth because satellites aren't too tightly packed, fly up into space again. The question is, how does it behave after that? And we need more information. So that's part of the motivation for that mission. There are other asteroid missions. The Indian Space Agency has considered some, as have a few private companies. But I don't think I'll have time to talk about all of them. So just to emphasize the current asteroid sample return missions, Hayabusa 2 is currently in flight, launched just under 2 years ago, looped by the Earth last year, and is now en route to Ryugu. It carries a lander package. It also carries a small explosive charge. The idea here is to test asteroid cratering by making an artificial crater. So you have a chunk of copper, you have a chunk of high explosive. You set this package down, and the spacecraft backs off to a very considerable distance. Set off the explosive, blow the copper into the asteroid, blow a hole a couple of meters deep. This does 2 things. 1, it tells us how the asteroid reacts to impacts. 2, it lets us take samples a couple of meters down, which may be different from the composition at the surface. So it'll take those 2 sets of samples, come back to Earth. And that's the launch for Tanegashima in 2014. OSIRIS-REx is to launch in just under 4 weeks. So this is a photo of the spacecraft getting final assembly at Canaveral. They are currently piling together all the stages of the rocket that it will use to ride to orbit, and from there to the asteroid. Once it gets out to Bennu, as I said, it'll map the asteroid, very precisely determine its orbit, touch down very briefly on the surface, grab samples, and come back to Earth. And then Dante Loretta, who runs this mission, will have lots of meteorites to keep him busy. But not actually meteorites, pristine asteroid samples. So those are scientifically motivated missions.
When you say touchdown, you have to match speed? Or
So these are blip rendezvous. The question is, are you matching speed here? Yes. If you want your spacecraft to survive the process, you go very, very slowly when you touch the asteroid surface. So it touches down very, very gently in microgravity, grabs material off the surface, lifts back up. The whole process is happening in millimeters per second because you can't go any faster and actually stay put.
so that means it has to fly the same orbit as the...
These go out to the asteroid, they match the asteroid's orbit, they stay there for a couple of years, and then they come back.
And it also has to follow the orbit to hit Earth, come back to Earth, so it actually does something like a similar trajectory as information as the asteroid itself. To hit the Earth, right? They have to bring it back to the Earth, right?
In this case, you're bringing the spacecraft back, not the asteroid.
Yes.
Make that clear. Okay, so that is scientific motivation. If you wanted to demonstrate asteroid deflection, you need considerably more energetic missions. So originally, in the 1990s, people talked in large part about deflecting asteroids using nuclear weaponry. Because if you're trying to move something a kilometer or more across, you need a huge amount of energy to do that. Now, we know that none of those objects are going to hit the Earth in the next few hundred years, so we can talk instead about much less dangerous methods of asteroid deflection. And so there's two that people have talked about. Kinetic impact deflection, which is to be demonstrated by the proposed AIDA mission, and gravity tractor deflection, which is to be addressed by the asteroid redirect mission. Was there a question? Okay. So AIDA stands for Asteroid Impact Dynamic Assessment, I think. Contrived acronyms have become very popular in both NASA and ESA, so we have interesting names for everything. But the idea here is to deflect an asteroid using a kinetic impactor. Now, a kinetic impactor is fancy sounding, but it is very simple. You just run into the asteroid with the spacecraft as fast as you possibly can. Spacecraft is carrying momentum. It transfers that momentum to the asteroid. Newtonian mechanics. Momentum has to be conserved. The asteroid's orbit changes. Now, there's some limitations to this, because how does the asteroid react to getting hit? If you hit it too far off center, maybe you just blow stuff off and most of the asteroid keeps on going on the same orbit. If you have some weird interior structure, maybe you blow up a lot more material than you expected in some large ejecta cloud, and you apply a lot more momentum transfer than you had thought. So we don't really understand how asteroids react to impacts like that.
Are you going to hit directly head on? Is it at an angle?
So the question is what direction do you hit the asteroid? Depends entirely on the geometry, in actual application, on the geometry of the orbit of the object. It's generally easier to run head-on into the asteroid as it's coming towards you. And the more velocity you have relative to the asteroid, the better in terms of changing its orbit. At other times, you may want to hit from the side or from some other odd angle, just to ensure that it doesn't hit the Earth in the most efficient way. But you still want to know how this works on an actual asteroid, rather than just talking about basic physics. So the AIDA project proposes to do this in kind of a clever way. There is a binary asteroid called Didymos. I showed you another binary asteroid before. Here is Didymos. That streak may be hard to see in the back. It's very small, but there's a satellite orbiting Didymos. There's no convention for naming asteroid satellites. Officially, the Didymos Alpha and Didymos Beta. Patrick Michel in France likes to call the satellite Didymoon because he has horrible taste in puns. Regardless, the idea is to run a spacecraft called DART into the satellite of Didymos, while another spacecraft called AIM, which has gone out there beforehand, matched the asteroid's orbits, watches the whole thing. So you see all the ejecta as it comes off. You can chart its sizes, all of its trajectories, and then you can measure how the orbit of the satellite changes around the primary. So the whole Didymos system will have gotten moved by this. But almost all of the motion is in the satellite around the primary. So this allows you to measure the offset in velocity much more precisely than you otherwise could. Now, this is in what we call phase A development, meaning that this very detailed design has been developed, and NASA and ESA have to elect if they're going to pursue the mission or not. That decision is pending. We'll see what happens. If the mission gets delayed by a certain number of years, it can no longer go to Didymos. But there are other binary asteroids that we know about from radar observations, so there's options for where this one would go. And none of those objects can hit the Earth anytime in the near future, nor can they be made into impactors by this demonstration. It's the first rule: don't create an impact hazard when you're trying to demonstrate how to fix it. So that's one technique for demonstrating asteroid deflection, which we hope can be demonstrated. The other technique is called gravity tractor deflection, and this is part of a much larger project that NASA is considering, called the Asteroid Redirect Mission. This developed as a compromise between several interests at NASA over the past few years. Interests in testing high-power solar electric propulsion, which is a very efficient technique for moving large masses of material around the solar system very slowly. It's not good for sending humans, but if you want to send humans to Mars, you could use this to send out lots of cargo beforehand so they had more supplies. The Asteroid Redirect Mission also developed in terms of the asteroid impact hazard community at NASA. We want to demonstrate ways of moving asteroids around. There's a proposal called the gravity tractor. This sounds like something out of Star Trek, but again, it's fairly simple physics. We have the asteroid. We have very weak gravity. The weight on the spacecraft might be equivalent to the weight of a piece of paper sitting on the table. It's very weak, but it's there, if we're hovering a few hundred meters above the surface. We aim the rocket exhaust off to one side, such that it misses the asteroid surface. If we can do the formation flying correctly, momentum goes that way in the rocket exhaust, which means the asteroid goes this way because as its gravity is pulling the spacecraft down, the spacecraft's gravity is pulling the asteroid up. We don't usually think of moving mountains by standing next to them, let the gravity pull them this way. But if you do this for months or years in space, where you have very low gravity to begin with, it does work. If you can do the formation flying, that you can have an engine that runs for months on end, and a large enough spacecraft. So the Asteroid Redirect mission proposes to demonstrate the solar electric propulsion techniques and the gravity tractor technique, and fulfill some interests from human spaceflight on NASA's side. NASA Human Spaceflight wants to demonstrate ways of equipment for human missions beyond Earth, Moon, space. To do this, you want to test out all the gear as best you can in Earth orbit, where here at the distance of the Moon, it's a few days back to the Earth, rather than a few months if something goes wrong. So the idea of Asteroid Redirect Mission is to go out to the asteroid. In this case, the current target is called 2008 EV5. If the mission gets delayed, if it still happens, again, there are backups. You land on the surface. You grab, in this case, not a couple of kilograms, which is the goal of OSIRIS-REx, but a very large block that would mass between 20 and 50 tons. Significantly more massive than the spacecraft. You lift it off the surface. And then you hover for several months because there's margin in the schedule and the fuel on the spacecraft. And very slowly, this now much more massive spacecraft plus boulder combo hovering out here pulls the entire asteroid this way. Now EV5, the target of this, is about 400 meters wide. Over a few months, they will move it in this design about its own diameter. Now 400 meters over a few months may not seem like much. But the advantage of this technique is that it's independent of the internal structure of the asteroid. All it cares about is the mass. And the deflection is a constant acceleration, roughly. So it grows quadratically with time. If you can apply a change that gives you a kilometer in a few months, that becomes 100 kilometers in a few years, and 10,000 kilometers if you have a couple of decades. So if we have a large asteroid that we need to move, and we have 30 years of notice, which the survey programs can provide, then this technique is much better controlled than the kinetic impactor. The kinetic impactor is faster, but you're never sure exactly what you're going to get. So the idea from NASA is to demonstrate both techniques. One is part of the AIDA project, and then gravity tractor is part of the Asteroid Redirect mission. Now, the plan for all of this currently has launch in 2019, 2020, which means we have to start building about now. Decision for this is currently pending between NASA and Congress. I have given up trying to predict NASA budget allocations in Congress. We'll see what happens if the mission goes forward. Again, it can go forward further in the future, just to a different target. But just to give you some reassurance that we do in fact have things that we can bring back, this is a radar image of the asteroid 2008 EV5, which I obtained as part of my PhD thesis some years ago now. That is a block sitting on EV5's surface, right near the South Pole. So EV5's shape is in many ways similar to Bennu. It's about 400 meters across, has a bit of a dent there. But the relevant thing for ARM is that there's these boulders scattered across the surface. So it's another rubble pile object like Yokawa, like most of the other near-Earth asteroids we've looked at. So ARM can go up there and grab stuff and bring it back. And ARM goes ahead, then you use this. This is a similarly composition meteorite, so it's about the right color. And you park it out here, and the whole asteroid goes that way. That's the plan. We'll see if NASA approves it or not.